One of the other things I wanted to talk about, which kind of relates to homework, but there is an application here to the professional world. So when you're working on a homework problem, here's one of the best things you can do after you complete that problem. Reread the problem statement and ask yourself the question, did I answer the question? So some of these questions are fairly involved in all the information it gives you. Sometimes they're asking for multiple things. Sometimes they want things in specific units. So it takes 5-10 seconds to just go back and just reread it and make sure you actually answered the question being asked. The way this relates to a professional atmosphere, in engineering, there's this idea of what's called the scope of work. If you're working in any engineering firm where you are in a consultative type of role and you're being hired by clients to do something, this is an idea that will have a lot of applicability. This idea of the scope of work, extremely important concept in the professional world. Maybe less so if you go into a field where you're not working with external clients. If you're building cars for Ford or something and all of your clients are internal clients, maybe it's not quite as important. But anytime you're working with outside clients, this is a big deal. So the scope of work, to boil it down, what am I being asked to do? And what am I being paid to do? What is in my contract? And one of the first steps of any project is to define that scope of work. So where do my responsibilities on this project begin and end? What am I responsible for, and what is somebody else responsible for? A clear delineation on that in engineering for building construction, like that I'm in. I'm a mechanical engineer, so I own the HVAC design. On any one of my projects, we also have an electrical engineer who has to provide power to all of our equipment. We might also have a structural engineer, and they need to make sure that that building's not going to fall down when they place my HVAC equipment on the roof. Well, my scope of work is the HVAC. It does not include any of that electrical design or structural design. But sometimes even within mechanical, there can be lines you have to draw where you say, well, this is my problem. This other stuff is not my problem. As a example for energy auditing, if I'm going to give a customer a proposal to tell them, this is how much I'm going to charge you to do an audit, am I looking at their entire building? Or if it's a very large campus, let's say multiple buildings, or am I just looking at one isolated piece of equipment? And so I need to define that, because if my contract says I'm only looking at this one unit, but then the customer says, well, I want you to also look at all this other stuff. And if I was a really nice guy, I might just do it anyway, but that can very quickly snowball. And now the customer's getting a lot more out of my time, and it could get to the point where now I'm spending more money doing this audit than I'm taking in from the customer. Bottom line, you don't want to do any work that you're not going to get paid for. And you really can't make a good plan of attack without having a properly defined scope of work. You need to make sure you understand the problem to come up with an efficient way to attack that. And so there is some applicability here between the homework and the professional world, this idea of the scope of work. The other thing I wanted to talk about today is to just look at a an example project where we did an energy audit and made some pretty substantial changes to this building and saved them a bunch of energy. This project was Tekoa Elementary, which is a super rural town, kind of between here and Pullman. You do have to take some side roads, but it's one of those towns that you don't get cell service in. Those rural communities have a really hard time finding money because they don't have a lot of population to pass bonds or levies or things like that. And McKinstry, we actually see a lot of these rural customers come to us for support. The building characteristics. So this was an early 1900s construction building. I think it was originally built in 1912, if I remember right. And then they did an addition in the 1920s or maybe the 1930s. But it's a very, very old building. Their HVAC, all they had was a single steam boiler with a bunch of radiators throughout the building. I don't have a schematic of this, but basically the boiler makes steam, and then throughout the building you have a bunch of steam piping, which eventually comes to these radiators. And as the steam sits in these radiators, they radiate heat. And that's really all there is to it. It's a very simple system in concept. You can see another radiator here in this office space, but that's all they had through this building. They didn't have any ventilation, which we talked about on day one. Providing ventilation is a big deal. They also didn't have any cooling systems. Now, the code does not require you to have cooling systems. It doesn't require you to have air conditioning. But in a school building, even if they close in the summer, it can still be very, very nice to have cooling for uh, really it's the beginning of the school year. So in late August and September, and at the end of the school year, right as we're going into summer, we can get some really hot days. And some schools, they just say, yeah, we don't need cooling. We'll just be hot for those few months. They had one thermostat for the entire building. This is more of a design question, but imagine having 10 or 15 classrooms. Ideally, each one of those classrooms should have its own thermostat. In this case, they just had a single thermostat that kicked that boiler on and off. McKinstry, we worked with the school and we helped get them a $1.7 million grant to help execute this project. So that is one of the roles that we play as an ESCO company is we're a consultant for the customer and we try and find ways for them to find grant money like this. A lot of these rural communities, they don't have much staff who can adequately navigate a lot of those kinds of discussions. These are the kinds of communities where we go there and their HVAC technician, so the man in charge of maintaining all of their HVAC equipment, he is also their groundskeeper and he does custodial work. And he's also married to the woman who runs the front desk. That's just the type of client that Tekoa Elementary is. It might be a little hard to see this, but this is a general floor plan of the building, so kind of an L shape here. And there were two floors to this building, but this is the main floor. So when we got there, they just had one thermostat right in the center of the building, which meant that you can see all these windows on the south side. And so as the sun goes around the south of the building and shines in all these windows, you can end up with these spaces overheating because this thermostat doesn't see that. It just knows how warm or cold it is in this hallway. So that's really not a good setup. Our goals on this project were to provide new LED lighting and a new ceiling. This customer really wanted air conditioning, and this boiler they had was run off of fuel oil. So they had a big storage tank underground that they would come and they would periodically have to fill it. They'd call some shop down the road that would come fill their fuel oil storage tank. So this is a case where they didn't have natural gas. We've been talking about natural gas being the primary fuel for heating a building, but the rural areas a lot of times don't have natural gas at all. So their options are either to go with an electric heating system, which is expensive generally, or with fuel oil or maybe propane to heat their building. And we wanted to give them better zonal comfort control, which basically just means more thermostats so that every single room has its own dedicated units. So to get that, we put in what's called a variable refrigerant flow, or VRF system. I'm going to have a lecture here maybe in a couple weeks where we go into a little more depth on VRF, so this will be a little more high level. What a VRF system can do, it can provide both heating and cooling using a building-wide heat pump system. So recall that a heat pump can provide heating and cooling using refrigerant. And it's using the same components, it's just reversing the process, whether it's in heating mode or cooling mode. What makes a VRF system very efficient is it acts as kind of a network. And what this means is that if you have some spaces that are in heating mode, meaning they want heat energy because they're getting cold, they can take that heat energy from other spaces that are trying to get rid of heat because they're in cooling mode. I'll talk a little more about that here in a minute. And this is an all electric based heating and cooling system. So what that means is that they will be completely off of that fuel oil boiler. And one thing about fuel oil is on a per BTU basis, it's very expensive as compared to natural gas. It's probably comparable to straight electric heat in terms of dollars, but it does fluctuate. It does fluctuate up and down a lot. Fuel oil is a very volatile uh, cost per gallon. So every time you fill that tank, you don't really know how much you're going to be spending. Another goal is we wanted to add ventilation air because they didn't have any ventilation before. And we did that with an energy recovery ventilator, also called an ERV. I'll have a picture of that here in a moment, but this is a fan system that provides 100% outside air, and it is a ducted system throughout the building to deliver that ventilation air to every room. The ERV also has to exhaust the stale air in the building in an equal amount because we can't pump in fresh outside air without getting rid of the old stale air. Otherwise, what will happen is you're going to start to pressurize your building, and eventually it will get to the point where your doors start blowing open. The other key part to an ERV, the energy recovery portion of its name, is that it can recover heat from the exhaust air that we're getting rid of and use that to preheat the outside air. And that will make more sense here in a moment. And ultimately, a goal is we want to save them energy. So that's a VRF indoor fan coil. This is a typical classroom. So in this building, there were probably 10 classrooms like this, where before they just had these steam radiators along the wall. It's out of frame in this picture, but often they're underneath the window. So we went in, we put in this brand new 2x4 grid ceiling that allowed us to put in new LED light fixtures, which are going to be very efficient compared to what they had before. And then these VRF fan coils can provide either heating or cooling depending on what this classroom needs. So inside this unit, this sticks above the ceiling about 12 inches or so. Inside of here is a refrigerant coil, and there's a fan in here that sucks in room air through this square grill. And then up above, where you can't see, it heats or cools the air depending on what we need, and then blows it out the four sides here. So you get this four-way throw of air in all directions. That's either hot or cold air depending on what the thermostat is asking for. And then that mixes in the room and comes to a neutral temperature, and then it sucks in more air through this grill and just keeps repeating that process. Another style of VRF fan coil is what we call a high wall unit. And so this would be used in a room where we don't install the ceiling. So these previous units, like I said, they stick above that ceiling about 12 inches. So you need some room to mount these things. You need some headspace to do that. If you don't have a ceiling, in this case, this was the principal's office, and it was in kind of an unusual location in the building. And to this hard lid ceiling right here was only about 8 feet, which is pretty low for a ceiling. And so if we were to try to drop that another foot by putting in a new ceiling, that would really start to constrain the feeling of that room. So instead, we put in this high wall unit. Underneath this plastic covering here is our refrigerant piping that goes to this unit. So if this unit wants heating or cooling, it's going to use this refrigerant to do that. And then you can see the thermostat, which its wiring is concealed behind that. That thermostat is telling this thing what to do. So you can look at this thing and see it's 73 degrees in here. And if the space is happy, then this unit will be off. But if it starts to get warm, then it'll turn the air conditioning on. If it starts to get cold, it'll turn the heating on. So we can see this unit right now is in cooling mode. This little symbol here is representing a fan. And so I think that this is telling us this is at high fan speed, because the fan will ramp up and down depending on how much heating or cooling is needed. And this picture, I think we can adjust how this throws air out the bottom here. So this unit actually takes air in from the top, which you can't really see, runs it through a coil, and then blows it out the bottom. All of these units get connected to some outdoor heat pumps. And so this is where the magic happens, I guess. So these heat pumps, what ends up happening in the summer months, so when we're really hot outside and we need to cool down the building, these refrigerant pipes covered up in these three white sleeves, these are going to pull heat energy from inside the building, because the inside of the building is heating up because it's summer and it's hot. And so we'll capture that heat in the refrigerant that's running through those pipes, and then we'll reject it to the outside. And after the refrigerant rejects the heat, it'll go back into the building where it'll pick up heat again, and it just keeps doing that as needed. And then in the winter, it's going to do the inverse. So we're going to capture the outdoor heat. So through these same units, we run the same equipment, but we run it backwards, essentially. And we're actually able to pull heat from the outside, even if it's cold out. Even if it's 5 degrees out there, there's still heat content in that air that we can pull out of it. It gets kind of hard to do, but it can do it. And then once the refrigerant captures that heat, then we send it back into the building, where we then deliver it into the space. And then it just keeps running through that cycle as needed. The energy recovery ventilator. So this is the device that provides our fresh outside air. And I wish I had a little bit of a wider shot from a little farther away, but hopefully I can illustrate this good enough. So what's going on here is this ERV is going to take in fresh outside air. So what you can't see off to the right, out of shot, is ductwork that goes to the outside wall. And so we're pulling in fresh outside air, and this is the path that it's taking, where it eventually goes up and then gets delivered into the building. But then I mentioned we also need to get rid of the stale air. And so this is pulling air out of the building that's, you could say it's used. It's already served its purpose. It's already ventilated the space and people have breathed it in and breathed it out. So that's going to be our stale air coming out. And you can see those two air paths actually cross in what's called the energy recovery core. I'll talk about that more here in a second. On the bottom here, you can see, well, it's kind of hard to tell, but there are two fans. And those fans are what's moving the air in each of those paths. So what's going on with this energy recovery core? Remember on day one, I talked about how energy intensive ventilation air is. Because if it's super cold outside, we need to heat that air up to a comfortable temperature before we send it out into the space. So let's say we have a very cold day and we're bringing in 5-degree fresh outside air, and we are getting rid of about 70-degree stale air. So that exhaust air at 70 degrees, there's a lot of heat energy in that air that a lot of times we just get rid of. We just dump it outside. But what we can do by passing those two air streams through this heat exchanger, and note that these air streams are entirely separated. So these air streams are not mixing, they are only sharing energy. They're essentially going through a series of interlocked plates to prevent the air streams from mixing, but the plates do share energy. So if you have cold outside air coming in and warm, stale air going out, what ends up happening is we can actually heat up that outside air, which also cools off the exhaust side. We get about a 45-degree temperature rise on each side of this heat exchanger. So now instead of having to take 5-degree air and heat it up to, say, 70, now I only have to take 50-degree air and heat it up to 70. So I've already saved a lot of energy by doing this. And we'll have a whole lecture on energy recovery that goes a little more in depth on this type of system. Here's an overall floor plan of what we went in with. This is mainly showing the ductwork and the VRF fan coils. So the red squares, those are all the fan coils that can provide heating and cooling. And now you can see every one of these has a thermostat noted by that T with a circle around it. And so this will control both of these units in parallel, and same with these two units, and so on. The green, so that's the ventilation air coming from that ERV. So that's the fresh air that we are delivering all throughout the building. And then the yellow, that's the stale air that we're pulling out of the space and sending back into that ERV. So right here, this is the ductwork going down into the basement. And so that's where that ductwork is that we were looking at in that photo. So you can see the supply and the exhaust are right next to each other. On the refrigerant piping side, and we usually show these on different floor plans because otherwise it gets very messy with our drawings. This is still showing the fan coils in red, so our heating and cooling units. And then in yellow, that is our refrigerant piping network. This is only one floor. This isn't showing the floor below. Um, right here, that's where the piping goes down to the first floor, and then it eventually goes outside to those heat pumps somewhere over here. But what this network allows us to do is for all of these units to share energy. So what can happen is on a moderately cold day, but it's still very sunny out, on this south side down here, you could get the sun just beaming in through these windows that will then say, tell these units, we need air conditioning in this room. Even if it's cold outside, the sun is just burning us up. And so this room might need air conditioning, whereas these classrooms back here that don't have that problem might need heating. So this room would be rejecting heat into the refrigerant network, which can then be used by these spaces out here. So VRF is a very efficient system because of that reason, because spaces in different operating modes can share that energy, which means ultimately the heat pump outside doesn't have to work as hard to get that heat because it's instead using heat that's already in the building. We're just kind of moving it around to wherever it's needed. I thought this was kind of a cool project. This is kind of indicative of the type of work that McKinstry does, and this was an energy audit we did that turned into this construction project, and it was a very successful project. It's a big win to find that $1.7 million in grant funds and to give them air conditioning and ventilation air. And this is probably the only building in Tekoa that is up to code now. And then this year, so this project was done, I think 2 years ago. And now this year we're looking at hopefully doing this very same type of system out at their high school. So that's all I got. Any questions on that or any homework questions?
So is that system mainly just used if different zones are going to be in different operating, like cooling or heating, basically?
Right. I mean, at any given moment, you can have zones in heating or cooling. What is another feature that's kind of neat about this is a lot of times if you have a heat pump system, the heat pump can only operate in heating or cooling. What this system can do is these can be in cooling, these can be in heating. You can have a mix and match through the entire building, which is a little unique because normally you can't do that. Normally it's kind of a, well, we all got to be in heating or we all got to be in cooling. If somebody's not happy with that, well, they're just going to get a little uncomfortable. The other nice thing about this VRF system that tends to lend itself very well to old buildings. I mentioned this is at least 100-year-old building. Those old buildings are really not designed for modern systems. Normally, we would have ductwork running through this whole building. However, which we still have some ductwork. That's how we get our ventilation air through the building. This VRF system with this refrigerant pipe, this pipe is very small. And so it's very easy to run this pipe all over the building, even when you have extremely limited space. Whereas if we went with a more traditional system that requires a lot more ductwork, less refrigerant piping, but more ductwork, we would need a lot more space to do that. Anything else? All right, I'll stick around until nobody's left. But otherwise, have a good night and a good weekend.
Thank you, Professor.
Thank you.